This one is even more exotic because, unlike the logarithm, it's a new function. It really is not any function that you can express in terms of the functions that we know already. And the approach always to these new functions is to think of what their properties are. And the way we think of functions in order to understand them is to maybe sketch them. And so I'm going to do exactly the same thing I did over here. So what is it that I can get out of this? Well, immediately I can figure out what the derivative is. I read it off from the fundamental theorem. It's this. I also can figure out the value at the starting place. In this case, the starting place is 0, and the value is 0. And I should check the second derivative, which is also not so difficult to compute. The second derivative is minus 2x e to the minus x squared. And so now I can see that this function is increasing because this derivative is positive. It's always increasing. And it's going to be concave down when x is positive and concave up when x is negative, because there's a minus sign here. So the sign is negative, right? This is less than 0 when x is positive and greater than 0 when x is negative. And maybe to get started, I'll remind you, f of 0, 0, it's also true that f prime of 0, that just comes right out of this. F prime of 0 is e to the minus 0 squared, which is 1. That means the tangent line again has slope 1. We do this a lot with functions. We normalize them so that their slopes of their tangent lines are 1 at convenient spots. So here's the tangent line of slope 1. We know this thing is concave down to the right and concave up to the left. And so it's going to look something like this with an inflection point. All right? Now, I want to say make one more remark about this function, or maybe two more remarks about this function before we go on. Really, you want to know this graph as well as possible. And so there are just a couple of more features. And one is enormously helpful because it cuts in half all of the work that you have. And that is the property that turns out that this function is odd. Namely, f of minus x is equal to minus f of x. That's what's known as an odd function. Now, the reason why it's odd is that it's the antiderivative of something that's even. This function in here is even, and we nailed it down so that it was 0 at 0. Another way of interpreting that, and let me show it to you underneath, is the following. When we look at its derivative, of course, is the function e to the minus x squared. So that's this shape here, all right? And you can see the slope is 0, but fairly close to 0, but positive along here. This is its steepest point. This is the highest point here. And then it's leveling off again. The slope is going down, always positive. This is the graph of f prime equals e to the minus x squared. Now, the interpretation of the function that's up above is that the value here is the area from 0 to x. So this is area f of x. Maybe I'll color it in, decorate it a little bit. So this area here is f of x. Now I want to show you this odd property by using this symmetry. The graph here is even, so in other words, what's back here is exactly the same as what's forward. But now there's a reversal because we're keeping track of the area starting from 0 going forward. That's positive. If we go backwards, it's counted negatively. So if we went backwards to minus x, we'd get exactly the same as that green patch. over there. We'd get a red patch over here, but it would be counted negatively. All right, and that's the property that it's odd. You can also check this by properties of integrals directly. That would be just like this process here. All right, so it's completely analogous to checking this formula over there. All right, so that's one of the comments I wanted to make about this. And why does this save us a lot of time if we know this is odd? Well, we know that the shape of this branch is exactly the reverse, or the reflection, if you like, of the shape of this one. What we want to do is flip it under the axis and then reflect it over that way. And that's the symmetry property of the graph of f of x. Now, the last property that I want to mention is what's happening with the ends. And at the end, there's an asymptote. There's a limit here. So this is an asymptote. And the same thing down here, which will be exactly, because of the odd feature, this will be exactly negative, the opposite value over here. And you might ask yourself, what level is this exactly? Now that level turns out to be a very important quantity. It's interpreted down here as the area under this whole infinite stretch. It's all the way out to infinity. So let's see. What do you think it is? You're all clueless. Well, maybe not all of you. You're just afraid to say. So it's obvious. It's square root of pi over 2. That was right on the tip of your tongue, wasn't it? Yeah. Right. So this is actually very unobvious, but it's a very important quantity. And it's an amazing fact that this thing approaches this number. And it's something that people worried about for many years before actually nailing down. And so what I just claimed here is that the limit as x approaches infinity of f of x is equal to the square root of pi over 2. And similarly, if you do it to minus infinity, you'll get minus square root of pi over 2. And for this reason, people introduce a new function because they like the number 1. And this function is ERF, short for error function. And it's 2 over the square root of pi times the integral from 0 to x e to the minus t squared dt. In other words, it's just our previous function multiplied by 2 over the square root of pi. And that's a function which gets tabulated quite a lot. You'll see it on the internet everywhere, and it's a very important function. There are other normalizations that are used, and the discussions of the other normalizations are in your problems. This is one of them, and another one is in your exercises, the standard normal distribution. Now, there are tons of functions like this, which are new functions that we can get at once we have the tool of integrals. And I'll write down just one or two more, just so that you'll see the variety. Here's one, which is called a Fresnel integral. On your problem set next week, we'll do the other Fresnel integral. We'll look at this one. These functions cannot be expressed in elementary terms. The one on your homework for this week was this one. This one comes up in Fourier analysis. And I'm going to just tell you maybe one more such function. There's a function which is called Li of x, logarithmic integral of x, which is this guy. The reciprocal of the logarithm, the natural log. And the significance of this one is that Li of x is approximately equal to the number of primes less than x. And in fact, if you can make this as precise as possible, you will be famous for millennia, because this is known as the Riemann hypothesis, exactly how closely this approximation occurs. But it's a hard problem. And already a century ago, the prime number theorem, which established this connection, was extremely important progress in math.